So I'm talking tonight about the physics of timekeeping, and it's promised from Stonehenge here on the left to atomic clocks. This is a modern atomic clock here on the right. And this covers really an enormous amount of science and technology and history. It's such a big subject that I have to be a little selective to find a path through all of it that comes off as fairly coherent and not just a listing of here's the thing and here's another thing and here's another thing. So to find a thread through this, I've sort of collected things around a particular theme. And so there could be a kind of an alternate title for this here, which is looking at the connection between timekeeping and place. And so, you know, another way of thinking about this is I'll tell you a bit about 5,000 years of timekeeping for navigation and the connection between when it is and where you are. So now I have on here on this title slide pictures of a whole bunch of clocks that I have around the house, and this ranges from, you know, a wristwatch here, the digital clock in our bedroom, and, you know, a clock in the microwave, and, you know, and here's my smartphone with a silly little augmented reality game going on it. But, you know, the thing that most of us probably think of first when you think about a clock is something like down here on the lower left, a mechanical pendulum clock. This is one that hangs in our dining room because the chime is really useful as a way to set time for activities with our kids. And this works as is a purely mechanical clock. And I have another example of that here from this building that is in the virtual background behind me. And, you know, in warmer weather in this picture here, this is Union College's Memorial Chapel. And this is a picture of the clock on the inside. And in particular, this is a close-up of some of the works of that clock. And this is a mechanical clock. It's a pendulum clock. And this sort of showcases the sort of central metaphor that I use when I talk about timekeeping, which is a clock is a thing that ticks. Right? In the case of a clock like this, it makes an audible ticking sound. If I shut up for a second, right? You can hear as the gears come together that characteristic tick tock sound that we associate with mechanical clocks, and that serves as a really nice metaphor for timekeeping as a whole. Right? A clock is a thing that ticks, that does some regular repeated action that you can count as a way of keeping track of how much time has passed. Now that tick is really obvious for something like a mechanical clock, but these are also relatively recent inventions. I mean, this is an old clock by American standards. This dates to around 1900, but, you know, just the invention of pendulum clocks happens in the 1600s. Right, so that's not all that long ago on the scale of human history, and we've been, as a species, keeping time for much longer than that. And so there are much earlier examples of clocks that look more like this. All right, this is on the lower right is the passage tomb at Newgrange up in Ireland near Dublin, and up here in the upper left you see a sundial. Right, and these are not things that you necessarily think of as being clocks, but in fact they are, because they do a regular repeated action that you can count to mark the passage of time. Right. Now, in the case of a sundial, right, this is the motion of the shadow cast by the vertical gnomon of the sundial. As you can see in this time-lapse video of a homemade sundial I made for an experiment in my backyard some years ago. This works because the sun over the course of the day rises eastish, right, moves across the sky and sets in the west, right? And that motion causes the shadow cast by a vertical object to sweep from west to east, right, to sweep in the opposite direction, right? This is a thing you can use to keep track of time. This is a clock whose tick is the motion of that shadow. By looking at how far it's moved, you can say something about how much time has elapsed. Now, in modern times, we know that this happens because it's actually moving. It's that the Earth is rotating, right? So if you imagine a person standing on the surface of the Earth, right, at some point they see the sun at its highest point in the sky. And if you're looking toward the horizon, there it is, way up there, right? And as time goes by, right, the Earth rotates and this person moves with the Earth, right? And so now they've rotated over to where the sun is setting in the west, right? And this continues, and then they're on the opposite side of the Earth from the sun. They're seeing the moon, they're seeing stars, and all that kind of thing, right? And then they come back around, see the sun rise in the east, right, and return to its highest point in the sky, right? That's one tick of the solar clock, right? You've marked out one day. The sun has done this regular repeated motion. It's moved all the way around and come back to the same place in the sky that it was on the previous day. Now, this seems like a very universal thing, but this is actually closely tied to where you are, because the exact position of the sun in the sky is going to depend on your location on the surface of the Earth, which is a sphere, right? So if you're standing exactly on the equator, right, it's possible that the sun at the center, at the midpoint of the day, is exactly directly overhead, right? But for other points on the Earth, it's going to appear in different places. Right, if you're in the northern hemisphere, as I am, and as London is, and as many of the people tuning in, anybody in the northern hemisphere, the sun is never directly overhead. It's always somewhere in the southern half of the sky, right? And that's because we're up here at some middle latitude, where the straight up to us goes off into space, and a line from us to the sun, right, is angled somewhat south. Right, and the reverse is true for anybody tuning in from Australia, right? The straight up goes off into space in the opposite direction, and a line from you to the sun is going to point in a somewhat northerly direction, right? At noon, at the middle of the day, the sun is not directly overhead, but will be either to the north or to the south, and that's why a sundial, the sundial in this little video, always casts a shadow, right? We don't have the situation where the sun's directly overhead and the shadow completely vanishes, because we're at a northern latitude, and that means that the sun's always in the southern half of the sky, and it's always going to cast a shadow that points in a northish direction. Right? So this is a way that you can keep time by using the sun, right? And this works great, but there's a complication to it, which is that exactly what angle the shadow points at is not the same at different times of year. And we can see this really dramatically if you go and you take a photo of the sun in the sky at the same time every day, right? This is, somebody did this in Kumagaya in Japan. And this is at different dates through the year, the position of the sun at 7 o'clock in the morning. And you can see that position changes. And as the year goes along, it traces out this sort of figure 8 shape. It's called an analemma in the sky, right? And so at different times of year, the sun is at different positions in the sky, right? This also happens because the Earth is a rotating spherical object. And in addition to rotating, it's moving around the sun, right? And the poles of the Earth are not, the Earth's pole is not completely vertical compared to the plane of the orbit that the Earth is in as it goes around the sun. It's inclined by something like 23 degrees, right? And that means that at different times of year, it's, it always points in the same direction in space, but at different times of year, it's pointed in different directions relative to the sun. So at some times of year, the North Pole is inclined away from the sun. At other times of year, the North Pole is inclined toward the sun. Right. This picks out sort of 4 special dates on the calendar. These are the 2 solstices, one in December and one in June. The December solstice, the North Pole is inclined away from the sun. The June solstice, it's inclined toward the sun. And then there's 2 equinoxes where the Earth is sort of perpendicular to that. Right, so the sun, it's pointed off to the side, and these are the March and September equinoxes, when the days are days and nights are exactly equal in length. Right? This motion affects the way that the sun moves through the sky and at different times of year. So if you looked at this, if you had the North Pole pointing, perfectly upright or on one of the equinoxes, you look at a point on the Earth from the perspective of the sun, you would see that point just move smoothly in a straight line across the visible face of the planet. Right. On the other hand, if you look at that at one of the solstices, when the pole is inclined toward the sun, you see this point seems to follow a curved track, right? It's moving sort of in a southerly direction as well, right? And this has to be reflected in the motion of the sun across the sky. So I said earlier that the sun is always in the southern half of the sky for someone in the northern hemisphere. So it rises sort of in the east, right? Moves up and to the south, and then, down and to the north to set in the west, right? But the exact path that it takes is different at different times of year because of this changing direction of the pole, the tilt and the changing direction to the sun, right? So in the summers, the sun rises well to the north of east, right? Goes up and to the south, and then comes back and sets well to the north of west. In the winter, right, the sun rises well to the south of east, goes yet further south as it moves up the sky, and then comes back and sets well south of west. So in addition to the motion of the sun from east to west across the sky that causes the shadow of the gnomon and a sundial to move, there's this motion north and south of the rising and setting positions along the horizon. And that's what leads to that analemma shape in the sky, right? This is also something that we've been tracking for thousands and thousands of years. And that's the other example of a very ancient clock that I had in that first slide. This is the passage tomb at Newgrange in Ireland, right? And this consists of, it's a giant artificial hill. It's about 100,000 tons of stone and dirt that have been heaped up to make this. And there is a narrow passage going into a vaulted chamber in the center of this mound. And that passage is aligned in such a way that once a year, or at the December solstice, the rising sun casts a beam through a notch over the doorway that passes all the way down that passageway. It's about 20 meters into the center. And that's the only light that reaches that central chamber all year long, right? This is a clock. This is a clock that ticks just once a year on the winter solstice, right? But this tells you, right, this is a repeated action that happens once a year that tells you, hang on, back up, that tells you you've come around again to the winter solstice. Right. And this is critically important information if you're living in an agrarian society, because you're dependent on, right, the natural world and the growth of plants and the motion of animals and things like that. So knowing where you are in the year is something that's critically important, worth putting a great deal of effort into to pile up all these stones and dirt to make this passage tomb, so that you have that information that, okay, on this date, when the light reaches this central chamber, we have now reached the winter solstice. This is the shortest day of the year in the northern hemisphere. From here on out, things are going to get better, right? The days are going to get longer. We're going to have more light. It's time to start preparing for spring. So this is an extremely ancient form of timekeeping. The Newgrange Monument was constructed sometime around 3200 BCE, so it's well over 5,000 years old and still functions perfectly as a clock today. You can enter a lottery to be one of the people in that central chamber on the solstices, though they are careful to note that it's Ireland, so the weather isn't guaranteed to be very nice in December, and if it's cloudy, there are no refunds. So these are examples of really ancient timekeeping technologies based on the sun. These are also things that are very bound up in where you are in a particular location, right? And that's not just because it's really hard to carry a solstice marker like Newgrange from one place to another, right? That's not a thing that you're able to do. It's not even really that easy to move a sundial. You can make portable sundials, but it takes, there's a trick to it. And those, even the portable sundials only work at particular latitudes, right, to tell you the time of day. But this is also, and there's also a major issue here regarding the position of people on the rotating Earth again. So, right, if we remember the motion of the sun across the sky, we see as, you know, the sun is at its highest point, then it's on the western horizon, then, right, it's completely hidden, then it comes on the eastern horizon, right, and we go round and round as the Earth rotates. That's you know, this particular sequence is seen by this gray person standing on our Earth here, who by the way is not to scale. And but there's other people on the Earth in other places on the Earth, and they're going to see something different at the same instant in time. This purple person is going to see a different time of day as you would measure by a sundial, right? In this first image, they see the sun just coming up on the eastern horizon, where it's already noon for the gray person, right? There's a different time of day for people at different longitudes. Now, this is a thing that we all know very well now, right? You know, we can, you know, you find any number of world maps that show the, you know, the whole map of the world spread out, and you can see the different lines of longitude and what time it is at different longitudes. Okay. You know, this is an issue that, you know, I've had to worry very much about today, right? It's evening in London, where this is hosted, right? So it's a nice evening there. It's the middle of the afternoon for me in the Eastern United States. And right, Lisa said at the beginning, you know, we have people checking in from Vancouver who are, you know, are still having their morning coffee, right? And, you know, there's people in Australia for whom it's already tomorrow. So there's lots going on, right? So there's this deep relationship between time and longitude, right? Now this makes time and timekeeping a useful tool, right? If you know what time it is in two different places, that enables you to determine the difference in longitude between them, right? Now, this, you know, that's not a hugely useful thing today, because we have these maps, we have these standardized time zones. We know I'm in New York, right? You're in London. There's 5 hours difference between us. We know that that's already set. We've all agreed to it, right? But a long time ago, this was a very big deal. Being able to determine the time in two different places and thus determine your difference in longitude was a critically important thing, as people were first really getting a sense of the Earth as a whole and mapping out the globe in its entirety. Now, to do this, right, again, we tend to turn to astronomy, but not to looking at the sun in the sky, because as we already said, the sun in the sky is in different positions at different longitudes, but looking at other things. A particularly useful form of this was looking at the moons of Jupiter. And this was pioneered by this fellow over here on the right. This is Giovanni Cassini, who was an Italian astronomer, but he was recruited to move to France. I changed his name to Jean-Dominique Cassini in the time of Louis XIV, and he helped set up the Great Paris Observatory there. One of the things that Cassini and his colleagues did was start to use the moons of Jupiter, discovered by Galileo in the early 1600s, as a timekeeping device to determine longitude, right? So what you have is, right, here's the planet Jupiter. These are the 4 Galilean moons that you can see. These orbit the Jupiter at with periods ranging from, you know, a few days to a couple of weeks, right? And so the pattern of those moons is constantly changing, right? And if you look at that pattern carefully, you can use the positions of those moons to say what time it is. In particular, there are fairly brief episodes where these moons are eclipsed, where they pass into the shadow of Jupiter and they blink out for a short time, right? And so you can use those eclipses to get very precise timing, provided that you know exactly what this pattern is. And this is one of the things that Cassini and his people worked out. The ability to predict when are these eclipses of Jupiter's moons going to happen, and thus use that as a timekeeping device. How is this used to find longitude? Well, you imagine, right, Cassini over here on the right. right, in Paris, and some, intrepid French explorer over here well to his west. What you do is you have those two people both look at the moons of Jupiter and record what time it is where they are. That is time as measured by the sun, right? They synchronize, they set their local clock to, 12 o'clock as the sun reaches its highest point in the sky. And then they use the time from that clock to record when did the eclipse of Jupiter's moons happen, right? So Cassini here says it happened at 4 o'clock. This fellow over here says it took place at 2 o'clock, right? That tells you that there's 2 hours difference in time between them because they're both looking at the same event that's happening a long distance away, visible from both places. Right. That happens only once at a particular time. That's a time that Cassini can calculate and say, all right, I know what time that should have happened. It should have happened at 4 o'clock for me. If it happened at 2 o'clock for him, that means we're 30 degrees of longitude apart. Right. And so this is how you can go and measure differences in longitude. Right. Now, this is a kind of extreme example, right? A 30-degree difference. 30-degree difference actually isn't all that plausible because that's somewhere in the middle of the Atlantic. You wouldn't do that very well, but this gets the idea across. And Cassini and his colleagues at the observatory used this to measure longitudes all over Europe and in France's various colonies around the world. They did this, they resurveyed all the borders of France in a way that made Cassini's boss, this is Louis XIV, commented at one point that he had lost more territory to his astronomers resurveying the borders than he had gained by military conquest. So this was a major project relating the time at various locations to the position. So you can turn this time difference into a position difference. This works really well because they're doing this in the late 1600s when they had already developed pretty good clocks. Now these are much more modern clocks. These are clocks. I believe this display is in Greenwich in the UK. And these are pendulum clocks from the last time that pendulum clocks were the best clocks in the world. And these, very much like the clock I showed earlier, are marking time by the swinging of a pendulum, which is a weight going back and forth. This is invented in 1657. Christian Huygens is the first to make a pendulum clock. And very quickly they become enormously good timekeepers used by astronomers all over the world for doing precision measurements. And this is the kind of tool that Cassini and his people had to work with when they're doing these longitude measurements. Now, how does this work? Well, it works on basic physics, right? A pendulum is essentially just a mass tied to the end of a string or a bar of some sort, right? And if you look at this, this might seem like it's going to be a difficult problem to work with because, we've got this force acting on this that's pulling up along this string, and we've got the force of gravity that by definition is pulling straight down, and there's all these curved paths and angles and things. This seems like a horrible problem. But actually, as you analyze the physics of this breaks down to something very, very simple. We can take this force of gravity and the force of the string and combine them together. And what you find is that the only thing you need to worry about to think about the pendulum motion is this little restoring force, this piece of the force of the string cancel, most of the force of the string and the force of gravity cancel each other out. And they leave just this little force that pushes the pendulum back and forth along this arc. And as long as the pendulum isn't swinging very wildly, then that force is very simple to understand. And it gives you a very simple relationship for the period at which that pendulum will swing back and forth, which depends only on the length of the pendulum and the strength of gravity. So those two things are easily knowable, right? And you can use that to say very accurately what period the pendulum will tick at, calibrate your clock. You can make excellent pendulum clocks relatively easily compared to anything else. So these are the tools that are being used to determine longitudes on land, right? This is a crucial thing, right? Louis XIV complained that he was losing territory to the surveying of his astronomers. They're surveying the borders of France on the continent of Europe, right? They're not able to do this, everywhere, right? They can only do this in places where you can set up a stable platform to have a telescope and observe the moons of Jupiter. They're in places where you have a stable platform where you can make your pendulum clock work, right? Because the one thing that really messes up a pendulum clock is having its orientation change, right? So, if you're on, say, a ship sailing from Europe to the Americas, right, that ship's rocking back and forth, that's effectively changing the orientation of this pendulum all the time, right? And that's going to cause the swing to get messed up, right? So a major problem, right, in the late 1600s, early 1700s, a major problem facing people who think about time and navigation and longitude and these things is, how do you do this at sea? Right? How do you do this when you're in a place where things are moving around, so that you want to know your longitudes, you want to know how far you've gone on your trip from France to the Americas, but you're on a ship and that ship's rocking back and forth. You can't really make a pendulum clock work very well on shipboard. So this is a major challenge. There are two solutions to this challenge. The more famous of the two in modern times is, one solution is just make a better clock, right? If you make a better clock, you can measure your longitude because you just set your really good clock when you're in Paris, right? And then you carry it with you and you always know the time in Paris. And then, you can do something on shipboard to say, okay, what's the time right now? By the sun. That's relatively easy to do. You can do that from the deck of a rocking ship. And then you compare those two things and your longitude. Right? This is a solution that's worked out by the English clockmaker, John Harrison. And this takes most of the 1700s. Right? Harrison finally succeeds in getting this to work in the middle of the 1700s. His first clock is this very complicated thing here on the left that has these pendulums that pivot back and forth. There's two of them going in opposite directions. They're connected by springs. There's this very complicated mechanism with the gears. They have this in the Royal Museum in Greenwich. If you're in the area, I recommend checking out, because it's weird and beautiful in the way that elaborate mechanical devices often are. And so it's a very, very cool thing. This worked very well. But his real tour de force device is this pocket watch here that you see him holding in this painting, and here's a photo of the actual thing, again in the collection of the Royal Museum, Greenwich. This is a project. It takes him 30 years to get the clock to work. It takes him another decade or two to get paid for it. It's all a very complicated and fascinating story of ingenious engineering and craftsmanship to make this thing work. But there's another way to do this as well, which also goes back to looking at things in the sky, which is another very common recurring theme in the history of timekeeping. And that is to look at the motion of the moon, right? So this is the other big, obvious object in the sky, right? The sun is the thing that's most obvious. It casts the shadows that make sundials work. Its motion along the horizon is what makes solstice markers work, right? But the other thing that we're all more or less aware of up in the sky is the moon, which changes much more rapidly, right? Once every 29 and a bit days, it goes through this full cycle of phases, from a crescent in one direction to a crescent in the other direction, right? And then in the middle is this, big circular object that's very, very bright up in the night sky. This happens, again, we know now, because the moon is, another spherical body orbiting the spherical Earth. And as it goes around the Earth, we see different amounts of it lit by the sun. All right, and that leads to this progression of phases that we see. But that also means that the moon is moving quite rapidly relative to the background of stars. So if you look at the moon through the course of the night, and you're an astronomer, and so you can compare, okay, it's at sunset, it's right next to this star, and then you look sometime later, it'll be farther away from that star that it was initially next to, and next to some different star, right? Over the course of a day, the moon moves relative to the stars by about 13 degrees in the sky. And over the course of an hour, it moves by about its own diameter. Right? So it shifts its position relative to the stars rapidly enough to be useful as a clock through the course of the night. Right? If you know where the moon is supposed to be in the sky, right, you can use that information to tell you what time it is. Now, this is also a story that involves a considerable amount of ingenuity and craftsmanship. One thing you have to do is be able to measure the position of the moon with some accuracy. And the way you do this is by measuring angles, right? You say, okay, here's the moon, right? This is some bright star in the sky, right? That whose position I know. I can measure the angle between this star and the moon by looking at by sighting along some object, right? And if I do that for a couple of different stars, I can say exactly where the moon is at this particular time, right? And then that is something that you can use to say what time it is, right? This requires some innovations in technology. The first way that people make these measurements is with a cross staff, like you see in the illustration here. But to do a really nice job of it, you need something like a sextant, and this is a sextant, again, from the Royal Museum collections, a tool for measuring angles between things in the sky. Right. The other piece of this is you need to know where is the moon going to be at a particular time. And that involves predicting the orbit of the moon, which turns out to be a really hard problem. There's a lot of parameters that go into the orbit, and the moon's orbit is not a simple thing, because the moon is orbiting the sun, the moon is orbiting the Earth, but also the Earth is orbiting the sun. So at some times of year and times of a particular month, the moon is closer to the sun than the Earth, and it's getting pulled on by the sun that way. At other times of year and other times of the month, the moon is farther away, and so the sun's pull is weaker. It's constantly being perturbed. It does a very complicated motion in the sky. This is extremely difficult to predict. It's not until Isaac Newton works out his laws of physics and system of the world that people even in principle are able to calculate this orbit. And then it takes a great deal of sophisticated mathematics to make that prediction. And then it takes a lot of hard, tedious work to turn that orbit into concrete predictions of where the moon will be at particular times. The guy who's responsible for that ultimately is this German cartographer, Tobias Meyer, who makes the necessary measurements of the position of the moon at various times to feed into the theory, and then does the mathematical work to make tables of these are the stars that the moon will be closest to, right, at various times for several years in the future, right? And if you have that information and you know where the moon is in the sky, you can use that to determine your time. And if you can determine your time, you can determine your longitude, because the tables are generated, for this is the time at which this would be seen in a particular place. So you know your local time when you see the moon in that particular place, you know the time difference, and that tells you the longitude. Meyer works all this out. The tables he produces are still a little too complicated for ordinary seamen to be able to use to find longitude. So they're converted into a more user-friendly form by the Astronomer Royal, Neville Maskelyne, who produces these nautical almanacs, right? And you can see, these are tables of what is the position of, in this case, these particular pages are giving the position of the sun, right? There's positions of the moon's node. There's, times of eclipses of the satellites of Jupiter for particular days in January of 1767, right? Maskelyne writes all this up in a relatively user-friendly form. They print these by the thousands. They distribute them to sailing ships, and this greatly simplifies the process of identifying your longitude for ships at sea. So, so between those two, right, there's this deep connection between what time it is and where you are, right, that is exploited to find longitude in these two different ways. And these, the story from Harrison's point of view, from the point of view of making the clocks and watches to do this, is famously told in this best-selling book, Longitude by David Sabel. And I would also recommend this. This is a more academic collection, but it's very comprehensive, and it has all the astronomy pieces of it as well. This is a collection by Richard Dunn and Rebecca Higgett that accompanied an exhibition at the Royal Museum some time ago. So this is an example of the connection between time and place spanning several thousand years, right? From things like Newgrange and sundials that are really rooted in place to one location to several thousand years later, right? People on ships at sea using this to develop techniques for finding longitude. Now, of course, both of these techniques of finding longitude, both the watches and the astronomical techniques, the lunar distances, both of those are completely obsolete now. And the technique that makes them obsolete actually has its origins in an observation made by one of Giovanni Cassini's colleagues in Paris back in 1670. This is a Danish astronomer who worked for a time in Paris named Ole Romer, who was one of Cassini's assistants, and he was given the job of measuring these eclipses of Jupiter's moons. And he tracked the eclipses of Jupiter's moon Io for a period of many years in the 1600s, and he noticed an odd pattern. That specifically, he noticed that there's Io takes a particular period; it's around 4 days to orbit Jupiter, and that the average time between these eclipses is very, very regular. Right? You can measure it. You measure the average time. It's just bang on over years and years of measurements of these eclipses. However, if you look at individual eclipses, what he found is that for some times of year, they happened a little bit early, right? A little bit early here meaning a few minutes, right? And if you looked at other times of year, each eclipse happened a little bit later than expected. Now, these sort of canceled out, right? So for part of the year, they got a little bit early, and then for another part of the year, they got a little bit late, and then, everything came around and around, and it all worked out fine in the end. But there's this change at different times of year. And Romer thought about this carefully and realized what was going on, which is that at the times of year when the eclipses were arriving early, the Earth was moving closer to Jupiter in its orbit. Right, so as the Earth's going around the sun, it moves from F to G here. It gets closer to Jupiter. As it gets closer, the eclipses come a little earlier. The times when the eclipses are showing up late is the other part of the year when the Earth's moving from L to K, when it's moving away from Jupiter. It's getting farther. Romer realized that what's going on here is that light has a finite speed. Right, the light, we only see the eclipse occur when the light from it reaches us at Earth. And as you're coming closer to Jupiter, the Earth is getting a little closer. The distance that light has to travel gets a little shorter each time, right? And that difference shows up as the eclipse arriving a little bit early. As you're moving away, that distance is getting a little bit longer. The light has to travel a little farther. It takes a little longer to get there. The eclipse shows up a little late. Romer's the first to realize in 1672 that light has a finite speed, and he actually makes a reasonably good measurement of it. That's within 10 to 20% of the modern value, right? So he's got a pretty good idea of what the speed of light is, right? That speed of light, that finite speed of light, is now the cornerstone of the time-based navigation system that we all use all the time. That's made all of these other methods obsolete. And that's the global positioning system. So now the global positioning system consists of a network of satellites that are orbiting the Earth, and each of those satellites carries a clock and a radio. Right? The clock keeps track of what time it is. The radio broadcasts a signal that tells you which satellite is sending the signal and what time it is according to the clock on that satellite. Your GPS receiver in your phone or a standalone receiver picks up signals from several of those satellites and uses those time signals to determine where you are. It does that because of Romer's observation that the speed of light is finite, that light takes some time. So if you know the difference in times that you see from several different satellites at different positions, that tells you your distance from where you are to each of those satellites, which then tells your position on the surface of the Earth. That might not seem obvious, but it's actually a thing that we use a lot, right? So I teach at Union College, which is located in Schenectady, New York. Hardly anybody knows how to say that or where it is. But when I have to tell people where we are, I can do it using time, right? One thing I can say is that we're about a 3-hour drive from Boston, Massachusetts. Now that means we are somewhere on a rough circle, right, in this part of the world, centered on Boston. That's 180 miles in radius. Okay, that covers a lot of ground, but I can also tell people that we're a 3-hour drive from New York City, right? And that places us somewhere on this blue circle that is also about 180 miles in radius, right? And there are only 2 places on the surface of the Earth where those 2 circles intersect. There's only 2 places that are both 3 hours from Boston and 3 hours from New York, right? One of them is Schenectady, the other is in the North Atlantic. So you can probably figure it out just from that. But if you really want to be pedantic about it, we can also say we're 4 hours from Montreal. And there is one and only one location on the surface of the Earth where all 3 of those circles intersect. So knowing the time needed to travel from one place to another can give you the position. And that's essentially what's going on with the GPS system, right? Your receiver is picking up the signal from several different satellites. It's using the differences between the times reported by those satellites to determine the distance from your position to each of those satellites. And then each of those satellites is in a very carefully maintained orbit that is known to extremely high precision. So knowing those distances places you on, a sphere of some radius centered on that satellite. And there's only one place on Earth where all of those spheres will intersect, and that gives you your position. Right? So this is making use of the fact that light travels at a finite speed. It was first measured in 1672 by Ole Romer using pendulum clocks. And now we use that relationship. We use that finite speed and these orbiting satellites to determine your position with incredible precision. Get your position on the surface of the Earth within a few meters. Right. Now, to do this, you need particularly good clocks. Right. The speed of light is the one situation in which American units are superior to the international system of units, which is light travels about 1 American foot in a nanosecond. So if you want to know your position on the surface of the Earth to within 3 meters, right, it's about 10 feet, you need to know the time to within about 10 nanoseconds. That requires a really exceptionally good clock, something well beyond the performance of any kind of pendulum clock. That requires an atomic clock. And so those satellites are carrying clocks that are based on cesium atoms. This is actually the modern definition of time, is that 1 second is the time required for 9,192,631,770 oscillations of the light absorbed or emitted as cesium atoms move between 2 particular energy states. Right. Now, quantum mechanics tells us that that's fixed by basic laws of physics. That energy difference between those states is fixed by basic laws of physics. That tells us that energy difference is related to the frequency of this light, and so we can take a microwave source in the lab and use it as a clock, provided that we know that the frequency of that is correct according to the cesium. How does this work? This is the picture of the cesium clock that I showed you before. The way these modern cesium clocks work, they start with several million cesium atoms cooled to within a few degrees above absolute zero by lasers, which is a fascinating topic, but that's a whole other long talk. They take those, they toss them up in the air, they pass through a microwave cavity where they interact with microwaves from this lab source that's going to be our clock. Then they fly up into the air, slow down, turn around, come back, pass through the cavity a second time, interact with the microwaves a second time, and then they measure the state of those atoms. If the microwaves you're using are exactly the correct frequency, then all of the cesium atoms will have gone from one state to the other state. If the frequency is a little bit wrong, some of the atoms will be left behind in the state they started in. And then you can tweak the frequency of your clock a little bit and try it again. And do that again, and then see, did we get better? Do it again. Did we get better? Right? And by constantly making small corrections to the frequency to keep it synced with the frequency that these cesium atoms want to absorb, you can make a microwave source that perfectly matches that frequency to such a degree that it would take close to 1 billion years to gain or lose a single second. This process may seem a little strange, but it's actually very much like what we do with an ordinary watch. So here's my wristwatch. If I want to know what time it is, I can go to some reference clock and I synchronize my watch with this. I want to test the performance of my watch. I synchronize my watch with the clock on the NIST website, giving the official US time. Then I wait a while, let my clock, let my watch run for 24 hours a week, something like that. And then I come back and I check it again against the official time, right? And see, are they still in sync, right? If my watch still shows the same time as the official US time, then I know my watch is working properly. If it's drifted off, then I do something to adjust the performance of the watch, and I repeat the process. Same thing that's going on in an atomic clock. You're sending the light up to the atoms up to interact with the microwaves. That synchronizes the state of the atoms with the state of the microwaves. They fly up in the air and come back down, freely evolving during that time. Their little internal clocks are running, right? And then when they come back down, they interact with the light again. And if the frequency is correct, that will complete the transition, and that tells us that the frequency is right. If the frequency is a little bit off, then we can adjust it and repeat. So the process by which these atomic clocks work is the same as the process by which you make a good wristwatch behave. Okay. So these cesium clocks are good to a second in hundreds of millions of years, close to 1 billion years. That's actually not enough for physicists. People are constantly working on doing better. And there are these experimental clocks based on strontium atoms and an optical lattice that claim things like a factor of 1,000 better than the clocks that are based on cesium, that are the backbone of this GPS system. So this history of timekeeping goes from these clocks 5,000 years ago, these clocks that tick once a day or once a year, to these pendulum clocks that are built in the 1600s that are good enough to measure longitude differences to very small differences, and clocks that are good enough to tell you that the timing of eclipses from Jupiter lets you determine the speed of light, all the way up to these atomic clocks that power GPS, that make it possible for us to play these silly little augmented reality games where you move around the city to different positions and find different things. All of that is several thousand years worth of history, and that history isn't over. We're continuing to invent even better and fancier clocks as we go. But that has already been a fairly significant amount of time out of your evening, so that I've been talking here. So I will sort of stop there and close, and I will be happy to answer questions out of the chat.